Sarah, for the intro. And Sarah and I were talking before that. So I learned to ride a bike after I wrote my first book. Most people do those two things in the other order, but so when people ask me what's harder, I'm like, yeah, riding a bike is just like reading a book. Once you do one, you can't forget it. Thanks everyone for showing in. So I'm bringing up the rear. This is your last talk of the entire week. You made it, so give yourself a pat on the back. And what better way to end a really informative, knowledge-packed 3 days than to have a really light conversation about particle physics, right? Really lighthearted and easy to digest. So we'll see. If you're here, hopefully you're here to learn about software entropy and how to reverse it. That's me, but Sarah already introduced me to you. So software engineering borrows a lot from other disciplines, other engineering disciplines, and even disciplines that are on the periphery of science, such as sociology and anthropology. It's natural. It's a very new discipline. So we build, as human beings, we build the knowledge that we already have. Almost everything is a remix of, everything is a riff of something else, and software engineering as a discipline being only so many decades old, it's almost natural that it borrows from all of these other disciplines. We are really good at remixing the knowledge from other domains and presenting it in new contexts. Off that, software engineering borrows a lot from physics. It lends a little bit too, obviously what with quantum computing and the actual synergy between software and hardware, but it borrows orders of magnitude more than it lends. Physics obviously has a huge influence on software engineering, not just with the fact that everything that runs software is powered by physics, whether they be transistors inside your computers, or, as you know, with quantum computing, as I mentioned, or even with some of the metaphors that we borrow, many of the metaphors that we borrow from physics. But we should take solace in the fact that a physicist of no less eminence that Feynman had kind words to say about software engineers. So he said that while the computer science is not as old as physics, understatement of the year, or of the century, it lags by a couple of 100 years. However, this does not mean that there is significantly less on the plate of the software, of the computer scientist than on the physicist. Younger though it may be, it has a far more intense upbringing. So reassuring words from one of the most preeminent physicists of the 20th century. One of the things that software does borrow from physics is the notion of entropy. Entropy in physics is a concept that pertains to the level of disorder in the system. So the entropy of an isolated system must always increase until it reaches equilibrium. That's often called the second law of thermodynamics. It is the bane of all people who want to invent perpetual motion machines. You cannot, in any system, the entirety of, if there's no external forces applied, no external energy comes in or leaves, then it must be that the disorder in the system ratchets up. It can only go in one direction, it can never go in the other direction. So there's almost like a ratcheting effect. There are different formulations of this law. Some call it the arrow of time. Time can never go backwards, but if it could, you could magically reduce the entropy of a system, but that is not allowed. There is a software equivalent of this law, which is where the borrowing comes in. Just the entropy of an isolated software system must also increase until it reaches maximum entropy, which means maximum disorder. And so while obviously the foundations of that are not rooted as they are in physics, but the law does uphold, and we'll see how and why it is the case that software systems left to themselves naturally progress towards more and more disorder. So before we do that, it's good to define terms. So what is software entropy? How would we define it? There are a few definitions in vogue out there. So here are a couple. One way to measure that is to look at the number of files changed within each commit. So that's an easy enough metric to look at. So if something is changing a lot, you can say its entropy, its disorder is a lot. So if one small change requires you to touch a large number of files, it's a measure that probably the level of disorder, that you can call it high coupling, or a lack of modularization, is causing a large number of files to be changed for a really one systemic change. Another definition is the ratio of unexpected problems to the scope of work. So this takes the notion of how we define work, usually in Agile or Kanban type teams, where we quantify our work in cards or tasks or stories or what have you. And this particular definition says the number of unexpected problems you encounter while doing the work you planned is a measure of disorder of the software system. So if you encounter a large number of problems that you didn't anticipate, chances are you have a high degree of disorder in the software system that you're working with. Those are all fine definitions, nothing against them, but I think something more organic or intrinsic, something that makes intrinsic sense is needed. So I gravitate towards the definition of entropy that comes out from Ron Jeffries' work. So anytime you're building a software system, there's some craft there. You're working your way around some obstacles. They could be domain obstacles, or they could be obstacles presented to you by any legacy software that exists beforehand, or time limitations, or what have you. All of you are in the business of creating software, so you know the constraints that you work with and against. Imagine a few of them in your way while you're delivering software. As you write code, as you build systems, you work your way around them. Sometimes you may remove them, but most of the times, the constraints are there for you to not break through them, but work your way around them. So things are still fairly straightforward. You can follow the logic, so to say, or follow the path while avoiding the obstacles. But things are not static. As we just learned in the keynote, the only constant is change in the universe. So the obstacles grow. They don't remain where they are. So now there are more, and then there are even more. So now, to just simply avoid the obstacles in your code, you have to take these increasingly circuitous routes. And the logic in your code, you can think in terms of dependencies or any metric that appeals to you, gets more convoluted. The complexity increases. And so this intrinsic notion, this intuitive idea that I'm sure all of you, if you've been doing this for a while, have experienced, it is not something that needs to be you need not be compelled to believe it. You probably have experiential evidence. This is a notion, an intrinsic notion that we can use to have a qualitative sense of what entropy in software looks like. So I define entropy as both this qualitative notion that we all experience and, of course, quantitative measures that we can also measure, we can quantify. So what are these qualitative and quantitative measures that, to me, add up to define entropy? Here are some quantitative measures. So the size of the software, and lines of code obviously is a dated metric, but you can actually compare across the same language. It's probably not good to compare languages with a higher degree of abstraction with something like C or Go with a lower degree of abstraction, but in the same language family, you can probably compare lines of code, and you can certainly compare number of files and the number of dependencies as a good indicator of size, the proxy metric for size. Volatility, that's easy enough. If you're using a Git repo or anything approaching that, which you really should be doing, then the heat map will tell you the volatility of each file or each module. Cyclomatic complexity, a well-defined metric that measures how complicated your software is. Coupling and instability. So if your software is highly coupled and therefore unstable, that's a quantifiable measure. And then cohesion. And there are several metrics such as lack of cohesion or tight or loose coupling of cohesion of classes that you can use. So these are all quantifiable things. In fact, static analyzers, tool analyzers will do it for you. So that's one component, one dimension, if you will, of entropy. There's also the qualitative measure. You can try quantifying this as well, but some of it is still going to remain subjective. The cognitive load for new developers. That's a qualitative measure, how easy it is for new developers to approach and comprehend your code. And conformance to the real domain. So if you subscribe to the domain-driven principles, how much are the abstractions in your software conforming to what the underlying domain, whatever business problem you're trying to solve, how tight is that conformance, or have you modeled your domain incorrectly? That can be used as a subjective measure to gauge entropy. So in my mind, all of it together gives you this heuristic notion of what entropy or disorder looks like. So if you can work with this definition, that entropy is the sum total of all of these things, then now we can address what the subject of this talk is, which is why does it increase over time? This original thesis that left to itself The disorder in software only ratchets in one direction. Why does it happen? So let's explore that. So I posit that there are a few reasons for this, and we'll look into that for the bulk of the remainder of this talk. The first reason that the entropy of a software system inevitably increases is the dependency forest. It's really not a tree, it's a forest. So this has in itself multiple reasons contribute to this. Number one, you can have too many dependencies. And number two, you can have a progressive lack of control with transitive dependencies. So you may control the direct dependencies of the software you're creating or modifying, but the transitive dependencies, by and large, are out of your control, because if you're, especially if you're using a third-party module that you did not author, if you are choosing to depend on a certain library or a framework, and that in turn depends on others, you usually have very little control of how far those transitive dependencies, and of course, transitivity can extend to multiple layers, you have very little control of how far that goes. Okay, so let's do a little exercise. This is a little bit of code to create a new React app using the Create React App node module. And I've suppressed the output because it creates a lot of stuff, so I just redirected the output to dev null. That's just to keep this slide manageable and fit it on one screen. But this creates my app. You cd into that, and you just list all of the dependencies. npm lsall, word count, wcl. There's an answer that is hidden. So I don't know if this is going to work, but if you want to try this, you can go to this and answer this, or you can shout out if any number between 1 and 10,000. The answer actually is a multiple choice answer, so we'll see that. Hopefully this works. Somebody could give me a thumbs up or thumbs down if the Menti is working. Okay? Cool. So it's actually, because of the presentation mode, it's going to be hard for me to show the Menti and the results, but that's okay. You can see the result. Anybody want to shout out the answer they typed in? Sorry, I can't show it to you. Just call it out, whatever you typed in, whatever you tapped in. 400? Anybody with a different number? 500? It's 3,114. At least that's what it was yesterday when I created this slide. No promises it's going to be the same today. This is literally a brand new React app created with no functionality other than what comes out of the box. And if you just list the node packages transitively, it is more than 3,000. That's a lot. There is already a heuristic notion of entropy you can sense. Any one of these packages that's out in node land changing materially affects this React app that you just created. So I love this old XKCD cartoon, which gives this humorous perspective on how every software looks like, and it's like a really classic example of Jenga or whatever that people were playing outside, some of you probably. And this one thing that some forlorn developer is creating is really holding up the edifice. And it's not a theoretical thing. That project could be LeftPad. How many people know of the LeftPad episode? Yeah, so for those of you who don't, there's this one developer. LeftPad, by the way, was a really small, this is the entire library. This is it, 11 lines of JavaScript. What it did is it padded, as you can read probably and make sense of it without me describing, those of you who can read JavaScript. It padded, left-padded integers to make them conforming length. And of course, every software in the node world used it, because it's such a common need to left-pad an integer to make it a conforming length. Due to some acrimonious debate between that developer and an organization that had taken copyright of one of the other projects, this developer unpublished the library one fine day and literally broke the internet, because virtually, I would say, every other node application somehow through a direct or indirect dependency used this. It was solved. I don't want to make this a scare tactic, because people recognize it, and this is where open source is great, and a copy of these 11 lines was republished under a new node package, and people changed their dependencies. The thing worked out in a matter of hours, but you can see the combinatorial explosion of one library that is widely used, either becoming unpublished or having some bug can affect. So clearly, this is a source of disorder. So what can we do in this phase? Creating a software bill of materials. So first thing you can do is to create an inventory of what your dependencies are. You can't control what you can't measure. So first of all, you should know what you depend on. And these recommendations come from NIST and their secure software development guidelines. You need to pin your dependencies. Don't be too permissive with these tildes and carets, which basically mean any compliant library that looks like this. That's a recipe for disaster, because if you want to pin to a library, pin to a specific version. In fact, they go beyond that and say, not just to a version, because somebody could update the library and not update the version. You should pin to a specific SHA, a specific binary that you depend on, so that that is there. And if you want to have an extra level of dependency, you should not depend on a public library repository such as NPM, which is, by the way, owned by a private organization. You should have your own internal repository of libraries, and then you should basically have the dependencies internally so that you're protected from that very sizable attack vector of somebody publishing a new version of that library with a new worm or bug or what have you, and now you have dragged it in with your dependencies every time you NPM update. So that's something that you can do. And enforce dependencies through fitness functions. We'll see that in a second. The bill of materials, it's a well-known concept. So NIST, National Institute of Science and Technology, I believe, has published these artifacts. These are great. They are a great resource. I encourage all of you to look at them on NIST.org. So it's a public website because it's funded by tax dollars. So it's open to everybody. And they have a very minimal set of the attributes of dependencies that an SBOM should have. So this is really a handful. It fits neatly on a slide, so it's not a lot. So they give good practical advice on how you should annotate your dependencies. And then they say here, somewhere they say that they, maybe not in here, that they say that dependency should be on a specific compiled version of the binary, not just a version number, because of the openness to the vulnerability that I talked about. Okay, so fitness functions, how can we do that? So fitness functions, and Neil Ford and others et al. Have written this book on architectural, the hard parts, and in it and other books, they have talked about how to enforce architectural constraints through actually executable code. All of us are probably familiar with and may have contributed to architecture diagrams and whatever your pet architecture is, whether that is distributed or microservices or layered monolith or whatever, we create all these diagrams and then they probably get ignored in the actual software that is implemented. So there are ways to overcome this disparity between what you claim your architecture is versus what it actually ends up being implemented in code through these fitness functions. So this is not really pseudocode, but it could be implemented that you could influence. For example, in a layered monolith, you can require that there are no incorrect pointing arrows, like the ADO, the service should depend on the data object, but not the other way around. Strict layering means layers should be unidirectional. So you can enforce that nothing is causing or dragging a dependency from the wrong direction by requiring that dependency count to be 0. So this is an executable function, just like any other test. It would run in your pipeline if it ever failed. If any developer, through carelessness or just not knowing, dragged a dependency in the wrong direction, this test would fail, and you would know they would know immediately. So this is enforceable architectural constraints. Okay, so what's another reason? Lopsided test strategy. So we all probably know of the test pyramid, which describes what I would think in pure economic terms, how an optimal test strategy should, what shape of the testing universe should result in based on an optimal, economically feasible test strategy. So tests at the top are harder, and then they take more time, they tend to be more brittle, UI-driven tests, and they tend to be also verbose. Therefore, there should be fewer of them versus unit tests at the bottom run super fast, they bring in fewer dependencies. You should write more of them, especially if you're doing TDD, you should be having a lot more of them. So this is what the optimal test strategy advocates. And of course, manual testing as needed, that's why that's the icing on top or the cloud on the top. But what happens is, over time, through a variety of factors, tests tend to bubble up towards layers that are more expensive, specifically UI-driven testing. Some of it is if you're using some of those point-and-click test strategy tools that if you have a user interface and you can just point to UI widgets and it generates the test scaffolding it takes a lot of discipline to not get carried away with that. It's really attractive user. It's very almost a seductive user interface that those test frameworks give you, that you can just point and click and generate a lot of test code. Sometimes that's the reason. At other times, because of the way the software evolves, it is conceptually easier to just say, I'm going to write an outside-in test, right? Clicking on the user interface and creating my test that way, rather than figuring out what the layer dependencies are and try to sneak the test in at a lower level, maybe at the service or even at the lower unit level. So this is potentially a test, a cucumber-style test that you might end up with. This is presumably a shipping website where at the checkout screen, you enter your shipping and billing address, and as you know, in most cases, you can say, my shipping and billing addresses are the same, so you don't have to type it twice. This test is asserting that behavior. So basically saying, when I click the checkbox, same as shipping address, as in use my shipping address for my billing address, then the billing address should be hidden. It should just utilize the same address. So it's testing that logic. Of course, you can do it that way, but is it the most optimal way to do it? You should ask yourself that question. Or can we drag the functionality of this test to lower layers? So here's another way, assuming that this is using JUnit semantics, but you can visualize this in the language of your choice. If the logic says that I should be using the billing address as shipping address, then I should be able to write a test at a lower level, which works with the domain object, which is the customer, assuming that customer has these addresses. So I should be able to use a builder pattern to say, create me a customer with the two addresses are the same, and then I can write an assertion that the shipping address actually equals the billing address. This is not UI dependent. This is at the level of the domain objects, implements the same logic, runs faster, is less brittle, and basically gives you the same assurance that the other test did. This is a strategy. Unfortunately, this is where the analogy with physics breaks down. In physics, we have gravity. Things naturally fall to the downwards. We don't have that much luck in our test pyramid. You have to expend force to drag tests down from these higher UI layers to these lower layers. This test won't write itself. You will have to extract and perhaps along the way refactor your domain objects so that they represent these abstractions that you're looking for. But it pays to do this. This is a way to reduce the entropy in your system. There is an awesome talk. I'm not going to play it. It's more than an hour long. But do take that QR code, that is the URL. It's dated, but it has aged very gracefully, which is more than I can say for myself. This is about JUnit, and this gentleman, he goes through an hour of coding to refactor a class with no test. So legacy code, Michael Feather's definition, right? Class without test. Writes tests for it outside in, refactors it, gets it down to the level. It's an hour, really great explanation. And at the end, he says, I could have done it in 20 minutes, which I believe him. I'm not going to question that. But I think that claim misses the point. It's not about the hour or the 20 minutes you spend doing that. It's about the cognitive load and the clarity of the code that you create that's going to save dozens and dozens, if not hundreds of hours for not just that person who does this, but also for all their teammates, because cognitive load, as we know, is where developers spend most of the time. You spend orders of magnitude more time reading code than you do writing code. So it doesn't really matter if it takes you 1 hour or 20 minutes. I don't think that's peanuts compared to the improvement, the reduction in entropy you will end up with by doing this. So do watch this talk, and you'll be more convinced on how to introduce unit tests where you have none. Okay, so let's look at the next cause. Progressive test anemia. That's another cause of why entropy in a software system increases. So what is anemia, the medical term? It's a problem of not having enough healthy red blood cells or hemoglobin to carry oxygen to the body tissues. And there are many different forms of that, each has its own cause. So it's, at some level, you can call it a symptom as opposed to a disease in its own right. It can be long-term or short-term, and it can be mild or severe, and it can be a sign of serious illness. So this is the actual definition, I believe, from Mayo Clinic. It's interesting, I find this definition as having very close analogy to how I would define test anemia. So test anemia is a problem of not having enough healthy green tests to carry the burden of finding issues. And again, there are many forms of this test anemia, and if you leave it unaddressed, it can cause serious software illness. So how does it happen? Over time, because of a variety of pressures. There can be scheduled pressures. There can be, I don't have time to write tests. I'm just going to fiddle with this one little line of code in production and push it through, and I know it will pass my green build, what have you. There can be a variety of pressures. Some of them justifiable, some of them less so. That can cause, and it's not just about coverage. Coverage is a little bit of a false indicator, but it's about lowered confidence in the behavior of the code. As I've said in my book, test-driven development is a way to increase your confidence in the code you write. It is not at all about coverage or even about the mechanistic notion of writing tests first, although that does help especially if you find yourself in undisciplined environments. But it's really about increasing the confidence in the code you create. So over time, your confidence goes down, and that's really what this anemia, not having enough healthy green test is about. So here's an example. This may be contrived, although it's from that URL, and the person who posted it on Stack Exchange claims that it's real. I adapted it a little bit. I basically shortened it to make it fit on a slide. But basically what this example does is there's some production code with a real method, and to increase test coverage, somebody, original poster claims they were not it, but they found it, wrote this fake method with a lot of lines of code, and then a useless test method to test the fake method to increase the test coverage. So if you just make a lot of lines of code and write tests to create those lots of lines of code, your coverage numbers look good. Now, obviously, none of you do that. I take your word for it. But however it may come about, this is not the way to solve anemia, right? This is not the kind of healthy green test. I mean, this is a useless test, so who cares if it's healthy and green? So this is what we are not looking for. This is a particularly egregious example. Whether or not it is real, it doesn't matter. If you get to a point where test coverage and other such false vanity metrics is all you're pursuing, then stop and think about how you can solve the underlying problem. Don't just fix the broken build. A broken build is a very important symptom, like anemia. But you would be very ill-served if that's all you obsessed about. Now, of course, if you broke the build with your latest commit, the easiest thing you can do is to revert your commit so that everybody else can commit, and that usually should really take seconds or no more than minutes. And then you can take your time fixing whatever you did. But in that sense, of course, keep the build green. I mean, I'm not saying keep the build broken and go home. That's not being nice to your teammates. Make the build green, but when you get it to green, the build is a symptom of something, right? The green is not, we're not chasing green. That's a symptom to healthy software. So what is that underlying cause of the lack of health or the higher entropy, if you want to stick to the physics metaphor? Focus on that. And of course, all of you have this professional hazard of showing up a talk with me. You're going to hear references to test-driven development. TDD, one of the things it does is it increases your confidence. It reduces that entropy at the point of origin, because there is, it's not really so much magic, it is about the discipline. There is no magic sauce, or if you want to talk about the magic sauce of TDD, it's really the RGR cycle. Because this habit of only writing enough production code to pass the failing test that you just wrote, this keeps you on the straight and narrow. And again, the focus is, people get antsy about it sometimes because it looks too, I don't know, draconian, 1984-ish or whatever. But the intent here is to keep you purposeful. At any one point, you should be able to answer the question with absolute clarity to yourself, what am I doing right now? And the answer is either I'm writing a failing test, I'm making the test pass, or I'm doing the refactoring post making the test pass. It should never be I'm just futzing around, because then you don't have the fast feedback cycle. Like, how will you know when you're done futzing around? Like, you wouldn't have a way of knowing. But if you do it this way, this ensures that inner fast feedback loop that as a developer, and developer quality is important to us, I know, it keeps you in that state of flow as a developer, because you always know what you're looking at, what you're doing. In fact, the way I like to do it is I can take a break at any of these stages, preferably at the end of a broken test. Sometimes if I need to take a break or a walk, I write a broken test and I step away from my computer, because I know exactly 20 minutes later when I come back, what do I have to do? I have to make that test pass. So it inculcates that discipline, inculcates that habit. So I would say if you want to get away from test anemia, try to give this a shot. Okay? The next thing we'll look at is over-engineering. So I want to start with a story here. So this is the mechanics of a regular automobile, a car wiper. a pair of wipers. All of you have probably seen that. Definitely the wipers, if not the mechanics. Actually, the mechanics are pretty straightforward. There is just one motor that connects with the rod and connecting rod, and there are a couple of pivots around which the two wipers pivot, and the whole thing just works like that. Okay? Cars have had this mechanism for literally decades. And it works, but if you are dissatisfied by what in this case is the northwest corner of the windshield that doesn't get wiped off, and if you are an exuberant engineer working for Mercedes in the 1980s, you would say, nah, this is not good enough. This is only covering roughly, 80% of the screen. I want to cover more than that. And if you have a lot of budget, and frankly, little else to do, you will do what Mercedes did in the 1980s with what they called their eccentric sweep. So that works. So they invented this thing, which is a single wiper, covers roughly 86% of the screen, of the windshield, but it has got engineering problems beyond what that simple system is. So number one, this is like so awesome, I want to play it again. Number one, the screen is rectangular, obviously, the windshield is rectangular. So the wiper has to extend in the corners, so they have to build that little thing that reaches out to reach the corners. That is not necessary in the simple two-wiper system. The single wiper must run at a higher speed to have the same effect, which means its motor needs to have both higher RPM and higher torque. So it's a more stronger motor, which makes for heavier gearing, and that whole assembly has to be more heavy duty. It does tend to break more often because mechanically it's moving fast. I mean, if you know mechanics, friction is a fact of life, it's a fact of physics. Higher powered motors tend to get hotter and run hotter. Mechanically, it's a more complicated system. So when it does fail, and it will fail more often than the simpler system, you are left with 0 wipers, which is a really big hazard. And more moving parts. So they realized this, and in 2000s, they quietly dropped it, this eccentric sweep, and then they did not have that. If you see Mercedes vehicles from after 2000, you won't see this. So what is our eccentric sweep in software? This is where if you have tomatoes, you should get them ready. Maybe this is our version of the eccentric sweep wiper. Okay, this is not a railing against Kubernetes. I use it, we all use it. But here's the deal. If you're talking about an orchestration mechanism to deploy your containers into production, and if you choose this, then you haven't just, as that meme goes, you don't just do Kubernetes. You have adopted a lot of cognitive load that comes with that. If you adopt Kubernetes, you must also adopt a whole lot of things. It's not a cheap shot at Kubernetes. You need to understand nodes and pods and kubectl and probably almost certainly Minikube, because you're going to somehow test it locally, so you need that. You need to understand that. You need to understand the control plane and its difference from the data plane. And if you're going to use templates, then you have to understand Helm and Helm charts and how the variables get in there. And then, of course, that brings an extra level of complexity for you. If that's the domain you're in, fine, then that's your solution. And by the way, Kubernetes isn't just a deployment orchestration mechanism. It presupposes that you can have pods with individual nodes, which means your original architecture must be decomposable enough to be deployed in that fashion. If you have a layered monolith, then maybe it doesn't even fit. Trying to put your right foot in a left shoe kind of a thing. So this is not a diss against any particular deployment mechanism. It is to say, decisions that have a higher engineering complexity have consequences. They bring this cognitive load, they bring this engineering complexity. If you adopt that, if you make that technology decision, be prepared to own the completeness of the complexity that comes with it. You can't have the cool technology decision, but say, I don't want to own the complexity. It doesn't work like that. I like to go back to the Agile Manifesto, and I love the way this is phrased. Simplicity, the art of maximizing the amount of work not done. It's worth dwelling on it. The art of maximizing the amount of work not done. That's the key. Think about how much work you can just either at least defer, if not outright abandon in your software systems and your work. And try to maximize that. Literally, the words have meaning here. You want to maximize that metric, the amount of work you don't have to do, because not having to do it means not having to redo it, maintain it, test it, all of those things. The other thing you might want to look at to get out of this over-engineering problem or tendency that we engineers have is to look at the concept of satisficing, which is a decision-making heuristic that emphasizes the total cost of decision, including the time needed to make the decision. So an analogy might help here. In baseball, at the speeds that normal pitchers pitch and the distance between the pitcher and the pitcher's mound and the batter, it takes about 0.4 seconds for the pitch, the ball to reach the batter. In that point, that less than half a second, the batter has to make these many decisions. Determine the type of the pitch to see which way it's going to curve, if it's a strike or a ball. So if it's a strike, you don't have to do anything. You can just let it go to the catcher. But if it's in the strike zone, then you've got to take a swing at it at least. Determine the speed of the pitch ball. So that's going to determine when you make contact. Finish the stride and get their foot down. So you have to take a stride. And then get the bat, obviously get bat on ball. And that's the part that matters. All in less than half a second. So imagine if the pitcher or the batter is a AI-driven bot and can do all those calculations in 3/4 of a second. It's worthless, because the ball would be in the catcher's mitt by the time the swing is taken. If your decision takes longer than the time that you have, it is worthless how accurate the decision is. It doesn't matter if you swung your bat exactly where the ball was 1/4 of a second ago. This is the concept of satisficing, the total cost of decision making. When you're making engineering decisions, or for that matter, any other kind of decision, it is important to look at how long is it taking you to make the decision and how long can you reap the benefits of that decision. And the perfection of that is gauged by the totality of that time, not that it takes me 6 months to decide the best orchestration strategy and I've missed all these other business or technical goals along the way. So that's another way you can quell the tendency for over-engineering. Okay? The next one we will look at is stuff we cannot foresee. How about a federal government shutdown? How many people are foreseeing that? This is no longer, sadly, a rhetorical question. So if you still have that, it's the same code. I think you should be able to go to the next. Do you see the next question or the same one? So you can just raise your hand if you're prepared for the government shutdown, if you're planning for it. So some of you are. Most of you can be forgiven for not doing that because, number one, as maybe a software developer, you'd think that doesn't affect you, especially if the government is not your client, then you're not really thinking about, am I going to get paid or not? But maybe you should. So in January 2018, the federal government did shut down. Hopefully it doesn't happen next month. Similar reasons because of a political impasse and preventing the passage of legislation of funds that are necessary to keep different parts of the government running, as you probably know if you've been following current events. Now, of course, that doesn't matter to most people. I mean, if you're creating software for a private enterprise, you're like, okay, well, it's sad. I mean, it may bother you as a citizen or a taxpayer or a voter, but as a software engineer, you're like, I don't care, it doesn't affect me. But it did affect us, the team I was in, because part of our continuous integration pipeline did vulnerability analysis. For vulnerability analysis, we look at the CVE database, Common Vulnerability and Exploits. That database is hosted by NIST. NIST is a government-funded organization. And it did go down on that day, and our build broke. So the government really broke our build on that day. So it may happen. So if you go back to that XKCD cartoon, that little dependency need not be a disgruntled developer. That could be the CVE database that you now depend on. So we say that it's stuff that you can't foresee, but I want to reframe that as 5 alpha. It's stuff that we refuse to foresee. Now that you know it, the excuse that I didn't know it goes away. So what do? Well, there are things that you can do about it. And if you see things this way, if you expand your threat analysis, then there are a lot more things that you can see that you previously might have thought, well, I could have never imagined that. There's more in your imagination than you give yourself and your teams credit for. So here's the last thing, and you can just shout this out. So here's the thing that you can foresee, maybe. So in JavaScript, in JSON, you can have a trailing comma. So if we define an array 1, 2, 3, comma, and you type it, it's got the 1, 2, 3. So if we parse the same thing as a string, how many people think this will parse correctly? Because clearly, defining an array with a trailing comma is OK. So can I parse an array with a trailing comma? How many people think it will work? I mean, none of you trust JavaScript to be consistent amongst itself. You're on the right footing. This actually gives you an exception. JavaScript is inconsistent. It's got two minds. It's kind of psychotic internally. When you define an array, it's OK to have a trailing comma. When you express the same thing as a string and then tell JSON to parse it, it says, no, I can't deal with trailing commas. These are the kind of things, it's a small example, but try foreseeing these things. If you have a software system that takes input from the console and people can type trailing commas, then it takes that, stringifies that, and then tries to convert it back, it will fail exactly there for that reason. And you have no excuse to not foresee that and take defensive action. Defend against the horrors that you can. You may be surprised how long that list is. You worry about the things, and there was a question in an earlier conversation about what do I do with X, Y, and Z happens. Put that aside and focus on the things you actually know about. You might be surprised how long that list is. Address that first, and then we can talk about the things that we really can't control. OK, so in conclusion, here are some of the things that we talked about. Dependency forest, progressive test anemia, lopsided test strategy, over-engineering, the stuff we refuse to foresee. Because really, there's a lot more of that than really stuff we cannot foresee. OK, that's all I have. Thanks so much.